Hello, I'm Sam at Gradle. When a software business is successful, it grows, adding more engineers, more tests, more lines of code. All of these things naturally tend to make builds slower, frustrating your developer experience. In this demonstration, we'll use data visualized on Gradle Enterprise's Trends dashboard to find and fix a serious build performance regression. Here we see various metrics relevant to build performance. The build count chart shows how many builds have been recorded and when. The cumulative build time chart shows us how much time has been spent executing all of those builds. The build time chart tracks mean, median, and percentiles of build time. Note how mousing over a particular day updates the legend to show just that day's figures. The serial execution chart shows how long the build would take with no parallelization. So you can compare the serial execution time with the build time to see how much benefit you're getting from parallelizing your build. The avoidance savings chart tracks how effectively work avoidance techniques like up-to-date checks and build caching are at saving you time. The build cache overhead chart visualizes the time overhead involved in getting the benefits of caching. It is fairly typical to see about 1 second of overhead spent to achieve between 30 and 60 seconds of time saving. But if something were impeding access to the cache, such as misconfiguration sending your remote cache request to a faraway node, you would see that here. Finally, the dependency download chart shows how much time is spent downloading dependencies. Now that we know what this dashboard shows us, let's use it to find and fix that performance regression. Scrutinizing the build time chart, we see that at first build time is fairly stable, averaging a little longer than 3.5 minutes. But then, right around here, something changes and the mean time jumps up closer to 5 minutes. So we can tell roughly when the regression must have happened. Let's narrow the time range and see what the performance dashboard can show us. This performance dashboard visualizes the same data as the trends dashboard, but from a slightly different angle. Clicking on build time to focus on just that metric, each column represents an individual build with taller columns representing longer builds. We'll try to figure out what regressed by comparing a build from before the regression to one from after the regression. This is the task input section of the build comparison view. The earlier pre-regression build is represented in blue. The later post-regression build is represented in green. Here we see which tasks had different inputs between the two builds. This is a particularly powerful tool for investigating build cache misses. But before we assume that cache hit rate is responsible, recall the avoidance savings chart from the trends view. If the decrease in cache hit rate were responsible for the regression, we would expect a decrease in avoidance savings. Instead, we see that avoidance savings have remained roughly the same. This suggests that reduced cache utilization is not the problem, although improving cache utilization can always be part of the solution. In this case, we can see that these Java compilation tasks had different entries on their class path. This suggests that the dependencies comparison could be particularly useful. The dependencies comparison shows us that between these two builds, an annotation processor was added to the build and made extensive use of. Annotation processors can be powerful tools, but can come with build time costs that aren't always obvious or understood up front. So in only a few clicks, we've isolated the source of the performance regression. This is actually quite an old version of the annotation processor in question from before it supported Gradle's incremental Java compilation feature. So let's upgrade to the latest version and expand the time range to see the result. We can see that build performance has improved quite a bit. The build gets almost as fast as it was before we used any annotation processor at all. So we get to keep the benefits of the annotation processing and have speedy builds. Frequently, build performance regressions go unnoticed until they've cost person days or even person years of wasted time. But do a couple minutes really make a difference? Let's say we're talking about a modestly sized team of 20 developers, each running 25 builds per day on average. The difference between a 3-minute build and a 5-minute build can be massive. Even if we consider only local builds, every dev is losing hours out of their work week. Over an entire year, the team collectively loses thousands of person hours. The key to saving these time costs is collecting, visualizing, and acting upon build data. Only then can we consistently achieve early detection and waste-free remediation of performance regressions. To learn more about this and other topics pertinent to having a fast and reliable software development toolchain, visit us at Gradle.com. In particular, check out our new book on developer productivity engineering. I hope you found this demonstration to be useful. Thank you for your time.